AWS CloudFront architectural capabilities. In the previous section, you saw how we can log into the AWS console and create a CloudFront distribution connected to an origin server, and you saw the entire thing working end-to-end using a browser. While we were going through the creation of the web distribution, we saw several architectural capabilities such as logging and monitoring, but there are other capabilities that I want to show you as part of this particular section. So the goal of this section is to go through a complete detailed list of all the architectural capabilities of CloudFront from the perspective of performance, scalability, availability, security, logging, monitoring, alerting, reporting, cost model, and interfaces. So let's look at performance. CloudFront uses several techniques to improve the performance of delivering content to the end users. It uses techniques like HTTP cache, keep alive connections, TCP slow start optimization, half-bridge SSL termination, DNS latency routing, and RTMP streaming. Let's look at HTTP cache. We already had a chance to look at the HTTP cache and the various HTTP headers that are honored by CloudFront and the edge servers. As you can see over here, the edge server, when a request comes in from the end user to the edge server, it goes to the origin, gets the content, and caches it. Subsequent requests are actually being served from the cache. That reduces a huge load on the origin server. So that clearly improves the performance of the system because the end user is talking to a local edge server, and also your origin server is not being impacted with all the unnecessary requests. Now let's look at performance from a keep alive connection perspective. So what is keep alive? Keep alive is a mechanism where in TCP/IP a client connects to a server and holds on to a connection so that it can make subsequent requests rather than opening and closing the connection every time, because opening and closing the connection is an expensive proposition. There's a three-way handshake in order to open a connection. As you can see over here, the first client comes in and it wants to talk to the origin server. Now what I'm showing you over here is what happens if there is no CloudFront. So what you're seeing over here is the origin server. We have the client. The client wants to get content. So the client sends a SYN to the origin server. The origin server sends a SYN ACK. And then the client sends an ACK. That's 90 milliseconds plus 90 milliseconds plus 90 milliseconds. Then the client sends the GET request, which is the HTTP GET request. Now you can assume that this time and this time is the same. That's actually almost the same time because it immediately after sending the ACK sends the GET request. And then assuming that the server, which is the origin server, responds back with the data, that's another 90 milliseconds. So it is going to take 360 milliseconds for the first user to get the response back. And if the second user wants to get the same content, the second user also goes through the SYN, ACK, and then the GET call, and then finally the server will respond back with the content. That's another 360 milliseconds. Now this is if you do not have any CloudFront. But let's say you have Keep Alive and you have CloudFront, and see if we can actually improve the performance of our system. Now let's see how Keep Alive makes things better. What you're seeing over here is the origin server. That hasn't changed. That's the load balancer for the origin server. We also have CloudFront, which is an edge server, and it is using Keep Alive connection. So this connection between the CloudFront and the origin server is a Keep Alive connection. And the time lag between these two is about 60 milliseconds. We know that from the location the client is to the origin server, it's about 90 milliseconds. So let's say the client is in Tokyo and the region server was running in Ashburn. That was about 90 milliseconds. But now we can break it down. Let's say that the client wants to get the content, so the client is forwarded to the edge server, which is also in Tokyo. The client connects to the edge server, sending a SYN. The edge server will return a SYN ACK. The client sends an ACK. Then the client also sends a get index.jsp. Now, while this is going on, the CloudFront server is also establishing a connection to the origin server. So you can almost think of 30 milliseconds for the SYN here, 60 milliseconds for the SYN over here, because the Tokyo edge server does not have anything in its cache. Again, 60 milliseconds back, 30 milliseconds back, 30 milliseconds into CloudFront, 60 milliseconds over here. So we have 30 milliseconds here and 60 milliseconds here, 60 milliseconds here, 30 milliseconds here, 30 milliseconds here, and 60 milliseconds here. So that's 90, 180, and 270. Although CloudFront is actually sitting in between and moderating the connection. Finally, the GET request comes in for the content, which ends up going to the origin. The origin sends the response back, which is cached, which is then put in the local cache, and then the response is back to the client. That's 360 milliseconds. Nothing has changed with Keep Alive connection for the first connection. But let's say the second user comes in. When the second user comes in, the second user will be connecting to the local edge server, which is the Tokyo-based server, because this user is also coming from Tokyo. Sends a SYN, that's 30 milliseconds. Gets a SYN ACK, that's 30 milliseconds. Sends an ACK, that's 30 milliseconds. And then sends a GET call, that's 30 milliseconds, and then gets a response back. So that's about 180 milliseconds. That's because the content is going to be served from the local cache. What you have really done is by having Keep Alive connection with the origin, you've actually reduced the network time. In fact, you've cut it down in half. And so you are actually seeing better performance for the second user and the third user and so on and so forth. So Keep Alive connection improves performance. CloudFront also uses TCP slow start optimization in order to improve performance. In order to understand TCP slow start optimization, first of all, we need to understand what TCP slow start is. TCP slow start is a mechanism that is built into TCP/IP internet to start slow before building communication momentum between the client and the server. When a client connects to the server, it establishes a three-way handshake, but then they don't start sending packets back really fast, even though they may have a fast internet. They start slow. They start by sending one packet, then two packets, then four packets, then 8 packets, and so on and so forth. And then they slowly build the momentum until they get to a point when there are no errors. That's how TCP/IP slow start works. It's a protection mechanism built onto the internet. Now, when origin sends response back to CloudFront, it can use TCP slow start. So let's see how we can use that. What I'm showing you here is origin, and we have CloudFront, and we have the first user, first guy. The first user asks for the content from the CloudFront edge server. Edge server does not have the content. So the edge server is going to go through the three-way handshake in order to get the content and then serve back the end user. But by this time, the origin and CloudFront have established a connection. And they've already gone through 1, 2, 4, 8, 16 packets being sent continuously in order to get the content back to the first user. When the second user comes on board, now there is a Keep Alive connection that is established between origin. I'm actually drawing the picture the second time over here. This is origin again. The second user is coming into CloudFront. There is already established connection between CloudFront and the origin. So now the multi-way handshake and all those things, 1, 2, 4, 8, all those things don't have to happen. They are continuously sending lots of packets together because now they've optimized their communication. The point I'm trying to make is by having TCP slow start optimization and keep alive connections, the CloudFront can actually serve content to the second, the third, the fourth, the subsequent users much faster. Once again, using TCP slow start optimization to improve performance of serving content. CloudFront also uses half-bridge SSL termination to improve the performance of CloudFront's secure distribution. In order to understand half-bridge, we need to understand the difference between half-bridge and full-bridge. Well, don't forget that CloudFront can also serve content over HTTPS, and it can use custom domains to serve the content. HTTPS uses TCP SSL, which actually adds on a whole bunch of other TCP/IP packets on top of your regular TCP communication on HTTP. Let's first look at full bridge versus half bridge. It's important to recognize is that in either case, the CloudFront, which is acting as the intermediary, which is acting as the edge server, is going to be serving HTTPS content. So whether it's full bridge or half bridge, it's going to be HTTPS. The client is always going to be communicating over HTTPS. As you can see, in full bridge, it's doing HTTPS. In half bridge, it's doing HTTPS. Client is always communicating with CloudFront over HTTPS. The question is, what about the connection between CloudFront and the origin? The connection between CloudFront and the origin can be HTTPS or it can be HTTP. Now, we don't want our end user client to come to origin over HTTP, but we can surely have our CloudFront, which is our partner, which is our CDN provider who's serving content on behalf of us, come over HTTP. By choosing the half-bridge option, by choosing half-bridge SSL termination, which is really clients coming into CloudFront over SSL or HTTPS, and CloudFront communicating with the origin over HTTP, having this particular feature allows you to improve the performance for the end user. CloudFront can use half-bridge SSL termination. It's one of the features that CloudFront has. It gives you better performance by leveraging the HTTP connections to the origin, because HTTP does not have as much overhead as HTTPS. And the half-bridge can take advantage of keep-alive connections between the CloudFront and the origin. So now we have double advantage. We can use TCP/IP keep-alive. We can use HTTP over HTTPS, which actually offloads several thousands of end users' SSL connections. That actually protects our origin server. CloudFront also uses DNS latency routing in order to get the end user to the right edge server. If you recall, AWS has something called Route 53, which is their DNS service. When an end user types in a URL in the browser, or whenever the end user is trying to access a specific resource, the URL has the host name. The host name has to be translated into the IP address, and that's where Route 53 or the DNS server comes in. Based upon the IP address from which the request went into the DNS server, the DNS server can recognize exactly where the user is located, and based upon where the user is located, and based upon several other factors, such as latency, the DNS server is going to send the user to the appropriate edge server. Notice if the user is in San Francisco, the user is going to get access to an edge server which is located close to San Francisco, not an edge server that is located in the East Coast. It's not going to get this edge server. It's going to get the one that is closest to it. And that is done by Route 53 latency routing. In other words, based upon which edge server has the lowest latency, it is going to route the user to the appropriate edge server. So DNS latency routing is also used in order for the end users to get to the appropriate edge server location. Now, it so happens that this DNS Route 53 is also used for optimizing which origin server to go to. For example, if a client ends up going to this edge server has to get the content, especially if the content was not in its cache. Now you'll notice that there are two origin servers. I have one origin server over here. I'm going to call it O1. I have the second origin server over here. I'm going to call it O2. So this is the AWS infrastructure. These are your origin servers. So origin 1 and then the origin 2. These are the two origin servers. The edge server has the opportunity to go to this origin server, which is in the East Coast, or the other origin server, which is located in Europe. The edge server ends up going to the origin server in the East Coast because it's the closest based upon DNS, latency-based routing. So the point I'm trying to make is DNS latency-based routing policy is used not only to find the appropriate edge server for the end user, but also to find the appropriate origin for the edge server to connect to get the content. When it comes to RTMP streaming, there are some specialized performance tuning that CloudFront has done. In order to understand the specialized performance tuning for RTMP, we need to understand progressive download versus RTMP streaming. Progressive download technology is served through HTTP, and in this technology, when somebody asks for a media, it starts to play the media immediately because it makes the request to the server, starts getting the content, and then it starts playing the media. But if you fast forward, many times I go to YouTube and then fast forward to maybe 7 minutes or 8 minutes into the video. If you ever do that, progressive download expects that everything up to that particular point in time is also downloaded, and then it'll play it. So it doesn't allow you to fast forward so that you can get to that particular content without downloading everything in between. Why bother downloading all the other parts of the media if it's not going to be watched? That's the idea behind RTMP streaming. RTMP streaming is served through the RTMP protocol, and here when a media is requested, it starts to play immediately, just like the progressive download, but forwarding to a point does not require everything to be downloaded up to that particular point. So this is much more efficient. And so CloudFront uses RTMP streaming mechanism in order to stream audio and video content. That makes it much more performant. We looked at several features that describe how CloudFront performs really well. There are also several features that make CloudFront scalable. First of all, there are multiple edge locations. There are close to 30 plus edge server locations worldwide, and edge servers are being added year after year. That is scalability for your application because now your application is even more distributed. And even within an edge location, multiple instances, that is multiple servers are in one location. And it actually uses the AWS scalable infrastructure in order to launch instances at edge sites when their loads become higher. It also uses a technique called collapsed forwarding, which is when multiple requests are being made at the same time. So let's say that 10 people are asking for the same content. Then in that case, rather than making 10 requests to the origin server because it came in at the same time, it actually collapses all those requests into one request. It's what is called collapsed forwarding. It has that feature too. And of course, half-bridge SSL termination that we talked about is not only good for performance, it also is great for scalability because now you don't have to have those millions of users terminate their SSL connection into your origin. Rather, it gets terminated right at the edge site, and all the edge site has to do is get the content for you and serve the content, still serve in an SSL fashion. So half-bridge SSL is also great when it comes to scalability. Availability. CloudFront also helps in the availability of your system. There are a couple of scenarios where it can help in availability. One scenario is going viral. Let's say you have a small startup and suddenly an article about your startup is picked up by a major news outlet or Twitter pickup, or maybe you did a social media campaign which has larger impact than expected. Now all the different users all over the world are coming to your site. Now you've suddenly gotten viral and you want to make sure that you support the load. Another scenario would be the partner is conducting a load test on your system. That also impacts your system. So these are all good scenarios. This means we have clients, that means you're growing. But then there's also a bad scenario, which is malicious DDoS attacks. Sometimes hackers try to do a distributed denial of service attack from all over the world. And in this way, you can actually, to some extent, mitigate the distributed denial of service attack by actually terminating the connections right there at the edge server locations. Security. CloudFront also helps in security. They have SSL termination, which supports SSL for serving the content. And you can also have custom SSL domains so that you can bring in your own SSL certificate and they'll serve it on behalf of you. They also support the half-bridge and full-bridge SSL termination. We like the half-bridge SSL termination because it helps in performance and availability of the system, and of course the scalability of the system. Also, there is PCI compliance. AWS CloudFront is PCI compliant. All their edge locations are PCI compliant, which means it supports processing and storage and transmission of credit card data. Remember, I mentioned to you that it can take a post form and submit the post form. So you can actually do your credit card transactions through the edge servers. That's not a problem at all. They are PCI compliant. And also, when responding to private cacheable content, you can rely upon the fact that they're going to be secure. There is also support for private content. You can authenticate users before granting them access to the content. Secure delivery over SSL, we talked about that. Flexible policy-based access control. You can have an access control policy that says who the users are. Use tokens in order to give them access to the content. You can restrict users based upon geolocation. You can whitelist countries. You can blacklist countries. We kind of saw that when we did the demo. There's also special security support for streaming. You can restrict the media content access based upon what is called price class. You can say only if they're coming from North America or South America can you have access to this particular content. This is what we call price class. They have that for streaming. They don't have very fine-grained control in terms of restricting through geolocation for streaming, but they have something called price class. You can also restrict access to object using signed URLs or signed cookies. You can restrict access based upon IP, URL path, or time range. And all these things can be configured for streaming in a file called crossdomain.xml for the Adobe Media Server streaming. When it comes to logging, logging can be turned on or off. And if logging is turned on, logs are placed in S3, in which case you're expected to supply the name of the bucket where the log files need to go. Logs are organized hourly. If no users access the content during a given hour, there'll be no log files generated. So if you only have users coming in for only the 2 o'clock hour and the 7 o'clock hour, you'll see only 2 log files. In terms of monitoring, the access log reports are consolidated and are available for monitoring through the AWS console. And the AWS console will show information for a specific period. For example, it'll show you reports for hours, days, or weeks. And also information is shown in a graphical fashion based upon the number of requests, data transfer, and error rate. Very good monitoring available on the console. And you can also use the API to get monitoring information. In terms of alerting, you can create alarms based on various criteria. Don't forget that these edge servers are running remotely and you don't really have access to the instances that are serving. You only get reports, but you can surely create alarms. You can say, hey, you know what? If you're getting so many requests within a certain period, or if you're getting too many bytes inbound, or if you're getting too many bytes outbound, or there are too many errors that are happening, I would like to know about it. And you can actually create criteria, and based upon those criteria, alerts will be generated and they'll be sent into SNS so that you can be notified. As far as reporting is concerned, several reports are available to you. There is the cache statistics report, which tells you the total requests that were made, the bytes transferred to the users, HTTP status codes, and also percent of requests that did not really finish downloading. This is an important number. This number indicates how effective your edge server is. If there is a content that people are just canceling the download and walking away, that means it's not fast enough. Maybe you need to reduce the content size, or maybe something else is going on. Maybe the edge server is slow. So that's a pretty important piece of information. There's also popular objects report. Lists the 50 most popular objects or URLs and stats about them so that you can tune them further, maybe increase the cache detail on those. There's also top referrers report. Basically lists the top 25 referrers, top 25 URLs from which the requests are coming in. There is a header called the referrer header. It so happens that the referrer header is misspelled in the HTTP specification. It's R-E-F-E-R-E-R, although the actual spelling for the word is R-E-F-E-R-R-E-R. That referrer header tells you from which URL did the user come to get to this URL that you're serving. There's that report. There's also usage reports, number of requests, data transfer by protocol and destination, and also viewers report that gives you all the devices that are coming in, the various kinds of devices, the browsers, the operating systems, and locations. So you can see whether your users are primarily using Internet Explorer, or primarily using Windows, or primarily using Firefox, primarily using Mac, or what is the breakdown. All those pieces of information are also available through reports. In terms of cost model, the cost model is a little bit complicated because there are so many components. There are three major portions to the cost model. One is the AWS S3 charges when the origin is in S3. So that's right here. If you're going to be putting your video, your images, your PDF documents, your HTML pages in S3, you're going to be paying a price for that. There is also regional data transfer out to the internet. Let's say your edge location is in Tokyo, then the users are coming in from Tokyo and nearby cities. All those users are being served content out. There's price that you have to pay for that. That's the regional data transfer out to the internet. And different countries have different pricing. So you have to think about that. That's the second portion. Then the third portion is submitting data to the origin. When users submit data to the edge location, which gets transferred out to the origin. Now, why would users submit data? Well, when the users are asking for a URL, if the edge location does not have that particular data, the edge location has to submit the request to the origin server to get the content. You have to pay for the submission of requests to the origin server. You don't have to pay for the data coming in from the origin server into the edge location. If your origin is within the AWS infrastructure, they don't charge you for any data transfer from the origin to the edge location. But they will charge you data transfer from the edge location into the origin. And don't forget, if you're going to be submitting forms, even then data is going to be going from the edge location to the origin server. It's not just the regular HTTP request to fill the cache. It's also for HTTP form requests because they're supporting delete, put, post, options, and patch HTTP protocols. So different components make up the cost. There are a few more components to cost model. There is invalidating requests. It's possible to invalidate the cache. For the first n number of requests to invalidate, it's free. I think n at this particular point is 1,000, but that can change in the future. So after n, you have to pay price per request for invalidation. There's also custom SSL certificate. If you're going to be using custom SSL certificate, there's a price for each SSL certificate. Also, based upon the choice of origin server, whether you are using the AWS infrastructure as the origin server or you're using the custom infrastructure as the origin server, there's going to be two different prices. If your origin server is AWS, no charge. But if your origin server is a custom server, there is going to be charge for the data transfer out from the origin server into the edge server. So you have to be careful about that. There's also reserved capacity pricing. If you reserve it based upon commitment that you're going to be using for the next 6 months or 9 months or a year, then there is better pricing that's available. In terms of interfaces, it's possible to create the distribution and manipulate the distribution using AWS console. AWS command line interface, and also AWS API. It's the same thing pretty much for all the different services, and that's true for AWS CloudFront too. So in summary, when it comes to CloudFront performance, CloudFront uses several techniques to improve the performance of serving content. It uses techniques like HTTP cache, keep alive connection, TCP slow start optimization, half bridge SSL termination over full bridge SSL termination, DNS latency routing policy, and RTMP streaming. In terms of scalability, it uses multiple edge locations, and these edge locations have scalable servers. They also use techniques like collapsed forwarding and also half SSL termination to improve the scalability of the application and the origin. In terms of availability, there are two different kinds of events that can affect the availability of your application. One is prevention from going viral situations where your application is being picked up by some kind of an organization, some kind of a social media campaign, and lots of people are now coming to your website, and now your site has gone viral and you have to handle the load. Or malicious DDoS attacks. In terms of security, they provide techniques like SSL termination, custom SSL to serve content using your own domains, PCI compliance if you have to serve private or confidential data to the end users through the cache, also private content, geolocation-based restriction. They have monitoring, logging, alerting, and reporting mechanisms so that you have a better understanding of what is going on in your system.